Hello everyone, welcome back to the Power Quality lecture series. In this video we are going to discuss one of the reason for waveform distortion, that is harmonics. And as you all know that harmonics is a main causes of power quality issues in the power system, and the harmonics are generated by use of a lot of non-linear type devices and electronic type devices in our power system. And deviation of the voltage and current waveforms from its ideal pure sinusoidal waveform of fundamental frequency, that is what is the effect of harmonics. Whenever a fundamental pure sinusoidal waveform is added up with some n integral multiple of harmonic content, then the entire pure sinusoidal fundamental frequency waveform will get distorted. So the power quality itself defined as it is the measure of deviation of voltage and current waveform from its fundamental pure sinusoidal waveform shape. And as you all know that in a pure polyphase system, which is expected to have pure sinusoidal alternating current and voltage waveforms of a single frequency, that frequency is known as the fundamental frequency. In our system it is 50 Hz. But in a real situation, this we cannot ensure this kind of purity, so that it deviates from his purity. Real voltage and current waveforms are distorted in real situation. Normally they are called non-sinusoidal waveforms. Whenever even if you are supplying with a pure sinusoidal voltage and current waveform, it is distorted due to these harmonics, and hence it is known as non-sinusoidal waveforms. So the non-sinusoidal waveform is formed with the combination of many sine waves of different frequencies. That is, we have a fundamental component, pure sinusoidal waveform, and it is added up with the combination of, means it is added up with many sine wave with different frequencies like 100 Hz, 150 Hz, and etc. So the actual power system signals have fundamental component as well as harmonic component. So the entire combination become like a distorted waveform. So you can, in a mathematical expression, you can explain the effect of harmonics. Suppose the F be the fundamental frequency in a current waveform, then fundamental current can be written as, that is, F is the fundamental frequency, so 1 into F, the first component or the fundamental component, is written as I1. It is the instantaneous value of the current I1. It is given as the maximum value I1 into sine 2 pi ft. F is simply 1 into F, the fundamental component. That is, the frequency is 50 Hz in our system. And if it is for second harmonics, means F become 2 into F, 100 Hz. So second harmonic component is 2F. So waveforms in a n-dimensional wave, n sinusoidal wave having different frequencies other than fundamental frequencies are called the harmonics. That is, waveform shape non-sinusoidal waveform is the sinusoidal waveform become distorted. It is added up with a non-sinusoidal waveform with a frequency of NF. N can be any integer from 1 to 3 etc. But in 1 means it is the fundamental frequency. That is what is our pure sinusoidal waveform. So we can write a current waveform which is a combination of n non-sinusoidal waveform shape, can be written as In, which is equal to In sine 2 pi n ft, where n is 1, 2, 3, etc. If n is 1, that is the equation is the fundamental component. If n is 1, it is I1 equal to I1 2 pi ft. And if n is 2 is the second harmonic component, n is 3 is the third harmonic component, etc. So if in a system consists of only the fundamental component, you can see that the system current or voltage is purely sinusoidal, which is not added up with any type of harmonics. But if it is added up with the second, third, fourth or seventh order harmonics, then the entire waveform shape will be distorted from its pure sinusoidal waveform shape. Hence, you can see that it is the system will consist of harmonics. So n is equal to odd number, it is known as odd harmonics. If n is even number, it is known as even harmonics. And suppose let us have a broad idea in mathematical sense, that is a non-sinusoidal waveform is constituted by, as we discussed, it is a combination of odd even harmonic component as well as the fundamental component. It will consist of the fundamental component, that is I1, plus it will consist of I2, I3, I4, I5, I6, odd and even harmonic components. The harmonic components means its frequency is NF. N can be any integer from 2, 3, 4, 5, etc. So thus mathematically it can be expressed as the non-sinusoidal waveform can be expressed as I is equal to sigma In, where n can be 1, 2, 3, 4, etc. And you can written as sigma n equal to 1, 2, 3, 4, etc. In sine 2 pi n ft, where n is 1 means the fundamental component, that is I1 2 pi ft, and if n is 2, it is I2 2 sine 4 pi ft, and n is 3 means I3 sine 6 pi ft, and etc. So this f is known as f1, the fundamental component. Second harmonic component is replaced here, the second equation it is replaced as f2. Third harmonic component is replaced as f3. Fourth harmonic is f4, etc. So the non-sinusoidal waveform shape is a combination of the fundamental plus second, third, fourth, fifth, etc. Even or odd harmonic components. So that is what is the effect of harmonics in your system. So here you can see a pictorial representation of the harmonic. Here you can see a green waveform, a green colored waveform. This one is actually the fundamental waveform, and this fundamental waveform means it is the first order component, that is 50 hertz, that is 50 hertz, and it is at a fundamental frequency waveform. And this waveform is actually, you can see that a 50 hertz fundamental frequency, the first positive half cycle during the 0 to 180 degree, and negative half cycle is 180 to 360 degree. And let's see what is third or fifth harmonic component. Fifth harmonic component is nothing but its frequency is increased by 5 times from the fundamental. That is the fundamental component is F. Then fifth harmonics is 5 into F. So you can see the fifth harmonic component is the red waveform. That means this frequency is increased means for the full cycle of the fundamental, you can see that this 5 times frequency increase means you can see 5 cycles inside this. That is you can see the red one, this first cycle, this is the second cycle, this is the second cycle, and this is the third cycle, and this is the fourth cycle, and this is the fifth cycle. So in a full fundamental waveform shape, you can see a fifth harmonic component means it will consist of frequencies increased 5 times, means in that full 360 degree there will be 5 cycles of voltage waveform. And seventh harmonics means in that particular 360 degree of fundamental waveform you have 7 cycles. You can see the blue line here. You can, this is the first one, this is the second one, this is the third, fourth, fifth, sixth, and seven cycle will be there. So what happened into the actual fundamental component in your system? You cannot see this as a separate one. So you will see the effective waveform only. You can see the combination of all this. So this fundamental green colored waveform plus this fifth harmonics component of red colored waveform plus this seventh harmonic component of this blue colored waveform is the actual waveform shape. That is what is actually shown here in a yellow color. This will be the final combined waveform you can see in your system. You can see this waveform only, that is the yellow colored. So what happened, this green colored pure sinusoidal waveform is now distorted with the reason. What is the reason? It is added up with this red colored fifth harmonic component, and seventh harmonic component current is added up with this green colored fundamental waveform, and now the waveform shape is like a yellow color. So you can see the how much distortion happened due to this kind of presence of fifth and seventh harmonic in this waveform. So that is what is the effect of harmonics. So you can see that you can use a Fourier transform to separate this fundamental plus harmonic component from this resultant waveform. You can use Fourier transform. So that is what is the harmonic, the effect of harmonics. Now we can see some of the terminology like interharmonics and subharmonics. Interharmonics and subharmonics. So it is nothing but interharmonics means that often in non-sinusoidal waveform there are harmonic having frequencies which are greater than fundamental but not integer multiple of fundamental frequency. That is now last slide we discussed about the integer multiple only. Now it is non-integer multiple. That means it is not 2 times, 3 times, 4 times. It is like 1.2 times, 1.3 times, 1.4 times. That is a non-integer type or fractional order frequency component. This kind of harmonic component is known as interharmonics, and which is greater than 1. So when n greater than 1 but not an integer, that is n equal to 1.2, 1.3, 1.4, etc. So like n is 1.2, I 1.2 sine 2 pi 1.2 ft. That component is known as interharmonic component. That is n is greater than 1 but not an integer. But what happens if n is less than 1? If n is less than 1, it is known as subharmonics. There are harmonics having frequencies which are smaller than fundamental frequency. This is known as subharmonics. That is, fundamental frequency is 1, the component of order 1. And if it is the order is less than 1, that is like 0.2, 0.3, 0.4, etc. That is n is less than 1, then it is known as subharmonics. So understand the concept of the interharmonics and subharmonics. Interharmonics is n is greater than 1 but not an integer. Subharmonics n is less than 1. So that is what is the effect of harmonics in the power system and its some terminologies. So we will discuss the next type of power quality problem in the next video.